In this video, we are going to look at this interesting problem that a lot of students find difficult to solve. We have the following: a pulley, which is just a cylinder, a rope that passes over the pulley, and two objects with masses are hanged at the two ends of the rope. One of the objects is called object A with mass MA, and the other one is called object B with mass MB. When released from rest, if MB is greater than MA, then object B accelerates downwards with acceleration AB, while object A accelerates upwards with acceleration AA. To analyze the problem systematically, let us draw a horizontal line called a datum line that passes through the center of the pulley. The displacement of object A from the datum line is XA downwards, and that of object B is XB downwards. The total length of the rope is L, which is equal to XA plus XB plus pi R, where R is the radius of the pulley. Pi R is the length of the rope that passes over the pulley. Since this part is a semicircle, the length of the rope over the pulley is equal to the circumference of a circle divided by 2, which is equal to 2 pi r over 2, giving you pi r. Now, over a time delta t, object A moves upwards by a displacement delta xa, while object B moves downwards by a displacement delta xb. If we take downwards as a positive direction, then we have xa greater than 0 and xb greater than 0. And we have delta xa less than 0 and delta xb greater than 0. The reason delta xa is less than 0 is because the displacement is upwards and we have taken downwards as the positive direction. The new displacement of object A from the datum line after delta t is xa plus delta xa. Keep in mind that delta xa is negative. The new displacement of object B from the datum line after delta t is xb plus delta xb, where delta xb is positive. Therefore, the new length of the rope is L dash equals to xa plus delta xa plus xb plus delta xb plus pi r. If the rope is inextensible, then we can write L equals to L dash. And therefore, xa plus delta xa plus xb plus delta xb plus pi r equals to xa plus xb plus pi r, which simplifies to delta xa plus delta xb equals to 0, which can be rearranged as delta xb equals to minus delta xa. Now let us check whether this equation is consistent. Object A moves upwards, and therefore delta xa is negative, and therefore less than 0. With delta xa less than 0, then we have delta xb greater than 0, which means object B moves downwards. Now, if we divide by delta t on both sides, we have delta xb over delta t equals to minus delta xa over delta t. And this simply is a relationship between the velocities of the objects. So we can write Vb equals to minus Va, where Va is the velocity of object A and Vb is the velocity of object B. Since object A moves upwards, we have Va less than 0. And based on this equation above, we get Vb greater than 0, which means object B moves downwards. So this equation is consistent as well. As you can notice, both velocities are equal in magnitude but opposite in direction. And this is expected because the rope is inextensible. By however amount object B goes down, object A has to go by the same amount in the opposite direction, and that means upwards. Now, if we differentiate this equation, then we obtain dVB by dt equals to minus dVA by dt, which is a relationship between the accelerations of the objects. Hence, we can write AB equals to minus AA. And here, AA is negative because AA point upwards. And if we plug this into this equation, we should get AB as a positive, meaning AB greater than 0. And this is consistent with our sign convention. This equation is also telling us that the magnitude of the accelerations are equal, but they are just opposite in direction. Now let us look at the forces acting on the objects and relate them to the accelerations. The forces acting on object A are the tension from the rope with magnitude TA and its own weight with magnitude MAG. The forces acting on object B are the tension from the rope with magnitude TB and its own weight MBG. Now, if we apply Newton's second law on each object, we have MAG minus TA equals to MAAA. MBG minus TB equals to MBAB. Now, since AB is equal to minus AA, let us rewrite the equations in terms of AA alone. If we do this, we have MAG minus TA equals to MAAA, and we have MBG minus TB equals to minus MBAA. In order for these equations to hold, we require some assumptions. So the first assumption is the rope is massless, and the second is that the pulley is frictionless. In order to simplify the calculation here, another assumption is also required, which is that the pulley is massless. Under the third assumption, we have TA equals to TB, meaning the tension is equal everywhere on the wire. And therefore, we can write TA equals to TB equals to simply T. Hence, we have MAG minus T equals to MAA, MBG minus T equals to minus MBAA. If we subtract the two equations, we can write AA equals to minus MB minus MA over MB plus MA times G. Since MB is greater than MA, therefore AA is negative. And this is consistent because by having AA as negative, it means that the acceleration of object A is upwards. Then for AB, we have simply AB equals to minus AA, and we can simply substitute this value into this equation, and we finally obtain AB equals to MB minus MA over MB plus MA times G. And for MB greater than MA, AB is positive, which means object B is accelerating downwards. And here it is, we have solved the problem.